This conference will now be recorded.
So today we are going to look at three different topics. And these topics will not be like classified directly in what we did before. So let's see one of the first topic, feature selection. Feature selection, if you remember, but what are the features? Can you tell me what are the features? What are the features in machine learning? For example, this iris data set. We have this data set. So we have columns and rows. So here we have the class. Here we have the class, and here we have column 1, column 2, column 3, and 4. We had four columns. So what are the features here, guys?
So the columns, 1, 2, 3,
exactly,
4.
Yeah. The columns are my features. So this one is the petal length, width, petal width, sepal length, sepal width, and the class. So what we want to do in some problems is that we want to reduce this number of features, like this example. These examples, we want to predict recurrence of diseases from genes. So we have people, some people here, each row is a person. And the features are the genes. What gene is present or not, for example. But we have tons of genes. I don't even know the number. We have a lot of genes present. And generally, to predict the recurrence of the disease, only few genes are responsible for it. Maybe just these 5 genes. All the rest will not predict it. All the rest cannot predict it. Only these 5 genes can do it. If we keep the entire data set, what will happen in this case scenario? If we have, like, I don't know, 23 genes or whatever, or 22, or we want to do this prediction, to run this prediction when we have only 5 genes that matter. What will happen with this data set? What will be the problem?
Time. Problem will be time.
First, yeah, time. It will take a lot of time to compute, to like build the model, because we have a lot of features.
And the resources
means a lot of parameters. And with a lot of parameters, the model will be too complex. Good. Then what would be the problem again?
The resources.
Sorry?
Memory. Resource.
Memory,
Yeah.
oh yeah, memory or processing power. Both will be a problem.
Yes.
Sorry, what did you say?
Testing.
What would happen in testing?
It's quite complicated, I think.
When it comes to the processing power here again, but so testing will be just dividing this data set in somewhere and use it as a test. Also, what can happen, guys, is overlearning or overfitting. If I to call it that way. Overfitting can happen because if these features are they don't really matter. And if we use them, then we might overlearn things that are not really generalizing. They might be here by chance. And this can happen because we have a lot of features. So if we combine the chance of every feature, we can get some rules that will make the model overfit. Especially that the more feature we have, the more complex the model will be. Do you agree with this? The more feature we have, the more complex the model can be, and the more, like we said in the first sessions, the more complex the model is, then what happens? What did we say about complex models and simple models? Come on, say something.
We cannot choose the right model or algorithm.
No, but what we said that is that we always prefer simpler models, those with less parameters.
Yes.
And if we have a model that is too complex, using a lot of parameters, a lot of features means a lot of parameters. And if we have something like that, then what will happen? The model is more prone to overfitting. So the smaller number of features, the better for the model. And the more generalizable it is. Are you happy with what I said, guys? Do you agree with me, or you don't know? Please tell me.
Is it the simple model would minimize errors as well?
Simple models is, if you prefer, the simple models have more chances of generalizing well in the testing set.
Mm-hmm.
Like we said last time, something that is simple, a simple rule, that is like a kind of the law of nature. Most physics rules, physics formulas are simple. They have like just 1 inch long, if you can see them, if you can remember some. The natural laws are just 1 inch long, you can see them. Like Newton's laws, Einstein's laws, all of them are just very small. Schrodinger's equation, all of these fundamental things are very small. And these laws are what generalize better. They tend to generalize better than the laws that are big, bigger than these formulas. Same thing is happening here. The more the model is simpler, meaning that it uses just a few parameters, the better it generalizes. You can understand it just by intuition. It's very intuitive. If, for example, you understand the law of like arriving late, and this law is very simple, say a person arrived late because it snows. This is a very simple law. Or another law that says this person is late when it is we are say in January, and say plus other parameters like there is like bad weather forecasting, plus there is a probability say that we are on a Monday, plus. So a law that says if it is snowing is probably going to generalize better than a law that is taking all of these parameters together, because maybe when combining all of these parameters together, we are just looking at one case. But when we find this simple law, it's probably common between multiple cases. Can you see like the intuition, this intuition? Can you see it? Amal, do you agree with what I said, or just a little
yes,
bit?
yeah. No, yeah.
Okay. So that's like the intuition. Something that is simpler is probably going to fit multiple scenarios and generalize better. But something that is too complex, maybe it will fit only few scenarios that we are seeing and will not generalize better beyond them. It's very like an intuitive concept. So here in this kind of problems, it's better if we remove all of the features that we don't need and keep only what we need.
So Reda, another question. So when we have a complex model, so how can we decide that now it's simple? Like when we remove the unnecessary features, or I mean, how can we know that now is simple and we can just go with it, go for it?
It's a spectrum, actually. There is nothing like it is definitely simple or definitely not simple. It is spectrum. We want it as simple as possible. We are not going to remove, like say, we keep just 5 or so. Maybe they are not enough. It's really problem dependent. So we try to make it as simple as we can. That's the goal. We want a model that is able to run excellent predictions, but to stay as simple as we can. So if we have two models, one is getting like 90% accuracy and using 100 features. The other one is using only 10 features and getting like 87% accuracy. I would really prefer to take the one with 87 accuracy and using only 10 features, because maybe it is going to generalize better in future than the one using 100 features. And it is like increasing the accuracy by only 3%. So it's like a trade-off. We want a model that is performing well, but the minimum one. And if we have, for example, 10 models, you are going just to rank them and see which one is simpler. That's all. It's just a ranking. Are you happy with my answer, Emil?
Yeah, thank you.
You're welcome. Are you happy, guys, with this explanation? It's a very intuitive explanation and very important. You really need to get it.
Yeah.
Okay. So the simpler the model, the better. So what happens, like when we just said that, this processing power required to train models with a lot of features, overfitting, and more difficult interpretability. Of course, when you have a lot of features, it's more difficult to interpret the results by human words, especially when you need to communicate your results to some audience, than for models that have like the one that has smaller number will be easier to interpret than those with a higher number of features. Okay, guys? So these are the problem why we use feature selection. And like we said, features are not all equal. Some are better, some are not so good. And there might be also highly correlated features, redundancy. For example, a feature in here and in here move at the same way. So if this feature, say, is 10, the other is always twice this feature. So if the one here is 10, the other one is 20. If this one is 30, the other one is 60. It means that one feature can be computed based on another feature, which means they are basically the same. Yes or no? Do you agree
Yes.
with this, guys?
Yeah.
This is also a problem. It's called feature.
Do you mean it's the same in terms of outcome?
Yeah, they contain the same information. They contain the same information. So if you know this, you will know the other one. So there is no need to keep them both.
Toda, I don't remember if you told us, I remember that you told us once that when we have like two correlated features, they can eliminate each other's. So better to choose one.
Yeah, we can eliminate one of them because they are the
it's
same.
like one eliminates the other if we let
It's
them.
not. It's probably you are probably talking about linear regression. About
yes, yes.
Okay,
Linear
I
regression.
will talk about this again. So if we have like two features, feature 1, x1, x2, and x3. x1 and x2 are highly correlated, meaning, let's say x1 equals always x2.
Yes.
So what would happen when we try to learn the features of linear regression? The coefficient, sorry. So this one plus this one plus this one plus this one, plus some constant here. So if this one equals, or let's just to simplify, this one equals exactly this one. x1 and x2 are always the same, just to simplify the problem. So if we say this is the coefficient here is 10, and this one is minus 10, and this one, say, is 3. When we look at this, we will probably say that this feature and this feature are more important than this. Yes, or no? Because here it's 10, minus 10, we don't care about the minus, we just care about the absolute value. But because they are highly correlated, what is happening? They are canceling each other. So if we put one here 100 and here 100, it's still, the equation is the same.
Yes.
And they are canceling each other in the equation. This is for linear regression, the effect in linear regression.
Okay.
The function will be correct, the regression will be correct. But when you communicate the results to the audience or to like the stakeholders, you will tell them that this is and this the most important, and this is just a small 3.
I don't quite understand why you took the absolute value of the second coefficient, because normally in this case, when you're evaluating your model, right, or when you're looking at the output, you probably look at the direction and if it's a positive or a negative association.
Well, I'm not sure I got what you mean. Could you repeat, please?
So you know you took absolute value.
Uh-huh.
Why did you do that? Because normally wouldn't you want to know what the association is, if there's a positive association, if there's a negative association, etc.
Yeah, but how much is the effect? When it is 100, the effect is big on the outcome. Even if it is negative, but its effect is big compared to this, even in a negative way. But it has a huge effect. If it was like, for example, -1, the effect is small, even negatively. So when I try to communicate the results, I will tell them that this is very important, and we try to get it down. If we want to maximize this value, this entire value, we want to get x2 down, and we want to get x1 down. But x3, we would say that x3 getting it up is not very important, because these values are not very important, are more important, sorry. This will influence the outcome more than this, but actually they are not, because they are canceling each other. Are you happy with my answer, or shall I elaborate something else?
I don't know. I don't quite get it.
But where is the problem?
I understand what you're trying to say. You're essentially saying we're looking at the magnitude of the coefficients, and then we're only concerned with those that actually have an impact on the. For example, if this was credit scoring, the third coefficient wouldn't necessarily have a huge impact on the credit score, whereas the first two would. And so you want to take the second coefficient because it's negative. You want to reduce that. You want to increase.
We want to increase this. We want to reduce this, and maybe and increasing this. But we would say that this increasing it is not as important as increasing this one and reducing this one.
So for example, x1 could be salary, x2 could be the number of loans or number of credit cards.
For example, like yeah. Mm-hmm.
And then x3 could be maybe having the like a landline telephone or something somewhat negligible in this case.
Yes, and we, because we missed out that these are correlated, we are ignoring the most important one, which should be this one instead of this two, because of this correlation. So this is like the point of like feature correlation inside the formula.
So do we only look at correlated terms?
We try. It's not that simple. We try to remove correlated terms. If they are correlated, we try to remove them, or you just do use L1. L1 will do that for you. When you do the regression, linear regression, you use the L1. The L1 will try to reduce these values, so you can have something more normalized. Sorry?
What's L1?
L1 is in the error cost. If you remember, we wanted this. This is the coefficients. This one here. There's some multiplied by some value here, C or whatever, minus
the regularization.
This. Sorry?
The regularization thing. The lasso.
Exactly. Yeah, lasso and reach, exactly. These are L1 is when you use the absolute value. So just to remove the sign, and we try to like have this coefficient to their minimum. Their minimum that can solve this equation.
Okay.
So this is what we use. So this way we can have these values like to the minimum. If they are correlated, what would be? What would the L1 will be? If x1 equal exactly x2, what would be this coefficient?
0, like the sum would be 0, right?
They could be 0. If they become 0, and this will stay 3, and this equation will not change, because this will cancel each other no matter what this value is, and this 3. This is 3. So you can tell that in your model, this one is the most important, and we don't care about this 2. It's like completely different interpretation, as you can see. Because of this correlation, we have produced completely different interpretations of what is happening. Are you happy with this explanation?
Yeah.
Perfect.
Yes.
And also, features are not all equal. Some are better, have a better predictive power than others. And some features can be just irrelevant. They do not contain any information. So that's why we use feature selection. So there are 3 classes of categories for feature selection. We have wrappers, filters, and embedded methods. Let's see what is wrappers. What are these wrappers? In wrappers, we train a model using only a subset of the features, of the available features. So we have some features. Some features, say we have 100 features here. My class is here. So what happened? I select only few features, few of them, not all of them. And I will train a model using only what I selected. And I measure the accuracy with testing of that model. I measure how good it is with testing or with the validation set of this model. And I do that with all the combination. And generally, we use a very lightweight model for it. We don't want to use, because we are building a lot of models. One model for each set of features. So let's say in the beginning, I use only the first one. Then I use only the second feature. And after completing them all, 100 features, I can use only the first one and the second one together. So, and etc. It's a combination. I combine them in multiple ways. So we are building multiple models. Do you agree with me? Please, guys.
Yes.
A bit of participation. We are building multiple models.
Mm-hmm.
Because we are building a lot of models, we want to use a simple model like a decision tree. Decision tree doesn't take a lot of computation. It's not optimization based. Unlike the SVM or logistic regression, they are optimization based. So the decision tree can be very fast. Mm-hmm.
Do we take decision tree because it's insensitive to normalization too?
No, not really. It's because it's fast, only because of that.
Okay.
It is sensitive to the size of the tree or other aspects, and it tends to overfit. But we use it only to see what features are good. So the best decision tree, the one that gives me the best score, more or less,
Mm-hmm.
is the one that uses the best features. We can safely say that. More or less safely, we can say that.
Yes.
The best decision tree will be the one that is using the best features, the best combination of features. And it is good. It's a good model, a good way to select features. But what do you think is the problem with this method?
I know it's like it takes time to execute the decision tree when we have big data.
Well, the decision tree is very fast. Generally, it's a fast algorithm. But we are computing a lot of decision trees. How many do we need to compute? We have say 100 features. How many decision tree are we going to compute to get all the possible subsets?
100 features.
We have 100 features, and we want all the possible combinations of these features. How many are we going to end up with? How many sets?
First of all, I think depends on the parameter. No,
but
how
we
many
should know the
parameters?
number of columns, no?
Yeah, we said the number of columns is 100.
100.
100 features is the number of columns. So how many combination can we have? Different combinations of features.
It's a very big number.
Yeah, it's very simple.
100x number.
2 to the power of 100. If I have 100 columns, 100 here element, 100 features. So if I take one, say we put 1 on it. If I don't take it, I put a 0. So 0, 0, 1, 0, 0. It means that I'm taking this one, and this one. And how many combinations do we have with ones and zeros? How many different combinations?
Yes, 2
2 to the power of 100.
Okay.
Each one have 2 possibilities. So it's 2 multiplied by 2 multiplied by 2. So it's 2 to the power of 100. I don't know if one of you can compute it by mind. Can you do that, guys? I can't.
It's a very big number, very big one.
But maybe I don't know. Maybe someone.
For me,
here,
I'm thinking differently. I am thinking that we should select, for example, 10 column for this 100 column. So it should be.
It could be anything. Well, if you start with 10, say you want to say I take only 10% of these columns, and then you go in the ones that are taking only 10.
Yeah.
So this will be, you can reduce the problem a little bit. You can do that. Yes. There is one problem. I will talk about it later after this method. With this, because it's another, it's the same way of doing it. So the search complexity is the main problem. With 1,000 features, we can end up with this number. So we need a search strategy like genetic algorithms, sequential forward selection. These algorithms are a searching algorithm with heuristics. Recursive backward elimination. It's a way of telling if we need to pick that feature or not, to test it or not. They are not perfect way. They don't test everything, but they are like guided into selecting or trying some features. So this is the problem of this method. But it is really like performance. It has like good performance when it is executed. It means that it gets you the right features. Now the second way, filters. The first way we call it wrappers. The second way it's filters. So it uses a statistical measure instead of a whole model. So for each feature, compute a statistical measure that tells how this feature is likely to predict the class. Thus, we test each feature only once. We don't need to do a lot of computation or like 2 to the power of n, but we take a feature and measure how good it is in predicting a class. What decision model is doing things that way? We have like my features. We have here my data set. I have here all of my features. This is the class. I take, for example, this feature and see how possible can I predict the class based on this feature. If I know, for example, this is mask. Let's take Batman's example. Mask, yes or no? No, yes. And here I have, so this is the mask. So does this, knowing this, does it give us like do we have a good chance of predicting this, the class? What the classification algorithm was using something similar to that? What classification algorithm was using something close to this? Close to this, what?
Decision.
Exactly, decision tree. Decision tree was doing exactly that. It was doing what? What kind of thing? It was using
like taking the root, yeah. Sure.
The information game.
Yeah.
It was trying to see how can we predict which variable is able to better predict the class. And then we divide it, and then we do the same thing again on the sub when we divide the data set again, and we keep doing this recursively. So it's the same thing, but we do it only once for each. It's like the first level of the decision tree. We do it only once for each element, for this one, this one, this one, this one, all of them, and we see which ones have like the high prediction power. Which one have the high prediction power to predict the class? If, for example, this can never predict the class, we never are able, where we are like we are able to predict the class based on this feature only in 1% of the cases. And here, 70%. It means that this one has a better predictive power than this one, because this one can predict it only for 1% of the cases. Okay? So for each we said that select only the best K features, and then we rank them by this prediction power, information gain, or whatever measure we are using. We rank them, and we take, say, sometimes the best 10% or so. And this can generally do a good job in practice, generally. So there are two ways, or there are other ways actually, not only these two. So we can study the correlation. How correlated is this feature with the class? It means how, if they, it's actually how predictable is this class based on this feature. Or we can use the statistical measures, like in the decision tree, information gain. We have also the chi-square, a famous measure, to just measure if we can predict as well this one based on knowing this one, and it will give us a score. Are you happy with this explanation?
Yeah.
Are you happy, Yusuf? You are always not happy, so I'm checking with you. He's not here.
No, I'm with you, but I'm not happy.
I'm able to predict you now.
Yes.
What are you not happy about?
Everything.
Wow.
No, don't worry. Just carry on.
No. We need to clarify things. I don't like to move on when one guy say that he's not happy, it means that probably 10 are not. So yeah. Did you understand the first way?
Yes, yeah.
Well, the first way is normally more difficult than the second way. The first way, we build the classifier with different set of features, different like combination of features, and the best classifier is generally the one using the best set of features. This is the for the wrapping. In filters, we just measure. We measure. We simply measure, for example, for this feature, we measure how predictable the class is based on feature I. And here it's I. So we measure, if you know correlation. Correlation, what we said, that one variable depends on the other. It's always like, if this change into one direction, this always change into some direction. This is correlation. It means that C equal M multiplied by some number, 3 or whatever, a constant number. This is kind of correlation. What correlation means. So if we can predict the class with some power based on this feature, when I know that this is a yes, for example, it's generally 70% of the cases a bad guy when he has a mask, for example. And if it is a no, say all 70% of the cases, he is a good guy. It means that when I know this, I can guess the class. When I know the mask variable, I can guess the class with a certain probability. This is what it means. You understand this?
Yes.
And if I take, for example, this feature, when I know it, I can very hardly guess what it is this. It means that this one have more power, more prediction power than this one. Because knowing this can give me a guess. I can say, if it is a yes, it has a mask, is probably not for sure, but he's probably a bad guy, because it's 70% of the cases. So this, it can give you like a hint It gives you a good hint when you know this. But knowing this gives you nothing. You can't really guess. This is like what we do in real life. When you know some feature, some information, it gives you a guess, not 100% correct, but it can let you guess. So this feature is important. But if it doesn't give you a guess, it means it's not important. It's not a good feature. Are you happy now, Yusuf, and the others, guys?
Yes, clear now.
For you are sure?
Yes, yeah.
Perfect. Oh, okay, guys, you're happy?
We're fine, Rida.
Yes.
Perfect.
Yeah.
So, and what's the difference between the first way and the second way? The wrapper. Can you give me just the differences that you can notice between wrappers and filters? Tell me, please, guys, what do you think is the difference between wrappers and filters?
Is the time of computation?
For which method?
The wrapper is took much
More
of time.
computation intensive. Mm-hmm.
Yeah.
Yes. Yes, this is one.
But also for this method using filters, we should calculate for each column, I think.
Yeah, but only one. For example, if you have 100 columns, it will be only 100 case.
Hmm.
It will be just 100. But in the previous case, we can have 2 to 100, which is a huge number compared to this one. And this is just a small measure. This is for each one of this, we compute a whole model. And this is just a measure.
Yeah.
But in terms of results, which one will probably give better results?
The other.
I would say
Wrapper.
filter.
Wrapper.
Filter.
The wrapper generally gives better results. Why?
But it's too complex, the wrappers, I think.
No,
Because I think the wrapper method it's correlate with others column, not like this.
Because I think the wrappers goes through all the features.
Yes, just to answer that, it's more simpler. This one is simpler, but we are not building a model yet. We are just assessing what features to use. So a simple model means better model, but here there is no model yet. It's just a trick to say what features are best. So simplicity is not really a strong, like something that is influencing a lot in this problem. We don't care if it is simple or not here, because it's not the final model we are building. We are just
Is it because we are optimizing better with the wrappers?
With the wrappers, the problem, we are optimizing better, but what is missing with the filters? If, for example, this feature is a very good predictor, and we saw that this is not a very good predictor, let's add another feature, this one. It is also not a good predictor. It's a bad one, say 20%. It is able to predict this case, this class with 20%, and this one just 10%. They are both bad predictors. This one is a 70%. But we will never know if we combine these two what will happen.
Yeah.
When we combine them together, we can have completely different results when they are combined. And the filters is not able to test this. The wrapper is doing all the combination possible, every combination. And it is testing these combinations. Because sometimes one feature looks very bad if you look at it alone. But if you combine it with another feature, the results can be completely different. That can go to like 100%, maybe. It can get 100% if we combine them. So the filter, it doesn't happen a lot in real life scenarios, but like the filter method is skipping these possibilities. It's like taking features independently. Okay? Are you happy, Yusuf? Are you happy?
No, not really. Not really.
No, I shout out to you. I'm happy that you say you're not happy. You are fine with when looking at a single feature and seeing how predictable is the class
Yes.
based
Yeah,
on one
that's
yeah.
that's okay. Yes.
Yeah. And like we said, the wrapper is testing all the combination, all the possible combinations. But I said that sometimes two features are bad predictors. Let's say they can predict the class by 10% success and 20% success respectively, these two features. But if we combine them together, meaning that we know this what it is and we know this what it is, sometimes the prediction can jump to like from this to like say 90%. If we know them together, knowing only one of them is not a big deal, but sometimes knowing them together can shift like the outcome dramatically. Can shift the outcome dramatically. So, and filters is not testing combinations. Filters is testing features one by one. Yes or no?
Yes. Yeah.
Yeah.
It's testing one by one. So it's missing on combination. If you know, for example, say, if he had a car here, and if he's or the gender of the person, like knowing if he has a car is not a good predictor for the class. Knowing the gender is not also a good predictor, but knowing them together at the same time, I think I need to come with a better example. We think in the next time with a better example with this case, but knowing them together, the car, the type, and the gender of the person can sometimes make the prediction much more powerful, not just the sum, not just the sum, but it can become a much stronger prediction than this one. And the filters is not checking this. Are you happy a little bit here, Yusuf, more?
Yes, more clear now. Yes.
Guys, please let me know. Are you happy?
Yes. Reda, isn't it expensive? Like computationally expensive to use the wrappers because we do all the combinations.
Exactly. That's the problem with the wrappers. We are doing all the combinations, 2 to the power of 100, and here only 100 computation.
But it's for better results, obviously.
Yeah, we get better results here, but in many cases it's not feasible to do all of this. We can reduce them a little bit with heuristics, like we said, but they generally gives better result than this. But in practice, we can go by this technique. It is possible, like to have good results only using this technique. Are you happy, guys, with feature selection?
Yes.
So this is with filters. Now the third method, and we have already talked about this, the embedded methods. Sometimes classifiers are equipped with a feature selection strategy, like what? The classifier itself has a feature selection way inside of it. Can you tell me of one algorithm that does it? Have feature selection right out of the box.
L1?
Exactly, the algorithm that supports the L1. Exactly. It is inside the algorithm itself, the optimization algorithm, and it will do the feature selection like for almost not for free, but almost for free.
Also, decision tree probably.
Not really. It's not doing. It is doing some sort of feature selection. Actually, that's true, but it's not super performant because it's trying to not use. It uses like features one by one, the best one, and go like till like the leaves are pure. So it does some feature selection indeed, but it's not like a perfect feature selection way. but still there is the feature selection. We saw that the decision tree tries to make the tree very small compared to like a bigger tree, and this will produce some feature selection.
What about KNN in terms of distance?
It doesn't have. I don't see how it can do feature selection because it's computing the distance based on all the features. So with KNN, we have to do a feature selection ourselves before using the algorithm.
So
are you happy, guys?
So we can use L1 and after use another model, like regression.
Sorry, what did you say?
For example, when we have like a big model, can we use like L1 for feature selection? And after
L1, we cannot use it outside of the model. It has to be inside the algorithm.
Yeah.
It's in the optimization function itself. It's that cost function.
Okay.
So the cost function is trying to build the model that gives the best accuracy, but at the same time we have the plus that term that is the L1. So we have, just to write it again, we have a term here that is how to compute the error rate for classification, plus something like C multiplied by the sum of the weights. So this is the L1.
Yes.
And this is the error, how much error we are making, the term for the errors. So it is inside the function, the cost function itself, the L1. So we can't use it before or so. It has to be used inside the algorithm. And you can get like a feature selection at the same time of building your algorithm when we use the L1.
So this one is for linear regression, but what I wanted to tell is like, can we use like linear regression, for example, for feature selection, and after that using another model?
You can do that. Yes, you can do that. That's a good point. Except that if you use strict linear regression, maybe it's not linear, so you get bad results. But still, you can get something. But L1 is not used only with linear regression. It is used with logistic regression and with the SVM. The SVM also can include the L1.
Yes.
So you can, for example, the SVM is very performant in logistic regression. You can try the SVM with the L1 and see what dimensions are used. You can there are ways of finding the dimensions that we are using, and you can have like a feature selection based on this. This is a good point that you said. Clever way of thinking. Thank you. Are you happy, guys?
Yes.
Perfect. So perform feature selection as part of the learning protocol. Cons can add complexity to the model while training. This is what I was talking about, like using L1 within a logistic regression or SVM. What time is it? Do you like a break, guys? Or shall we continue?
Yes, please.
A break. Okay, let's have a 15 minutes break, and we will come back.
This conference will now be recorded.
So this is a famous problem, the class imbalance. So let's consider a data set with 90 examples for class A, and another class with just 10 examples. If we have a model that can predict everything as class A, we will get an accuracy of 99%. And it is not even like a real model, it just classifying everything in one class. And just using accuracy is not a good way of measuring the performance of such model. Do you agree with me here? Do you agree with what I said? And do you understand the problem?
Yeah.
So this class imbalance, and how do we need to address it? So maybe this class is very important, class B. And if we are not detecting it, then we are not really building a model or a useful one. So how to solve this problem? So we have two famous ways, the undersampling and oversampling with the replacement. So the undersampling, so this is the majority class, and this is the minority class. What we do, we take some representative samples from this big class, say this group have just one example, here and then here, and so we reduce its size from this to this. So they become similar in terms of size. So this is undersampling, reducing the size of the big class. And we have oversampling. Oversampling, we take the small class. The first way, we just duplicate its like samples. Every example is duplicated. So we take one and we duplicate it in all of these places. So what is happening here when we do this direct oversampling is that we are just artificially increasing the error for this class. Because when we compute the error, we compute it for every example. So every example that is misclassified is an error. And if we duplicate them, it means we are just duplicating, making the error for this class bigger. It's like multiplying the error of this class, which was in the previous example, it was 99% accuracy in here and 1% in here. So when we do that, we are duplicating this accuracy. We can do this for the error, which is the opposite. We are duplicating the accuracy that was 1%. And if we multiply it by 99 case, it will be multiplied by 99. So this will be 99, this will be 99. So they will become both 50-50 because they are the same. So what we are doing is just artificially multiplying the error of this class by the number of how this sample is multiplied by. So if it was 1 and we multiplied by 99, we are just multiplying its accuracy by 99. It's like we are changing the weight if we just duplicate things. Do you agree with me, guys?
So when we are duplicating these errors and when we're computing them, it's basically the misclassifiers.
We are duplicating everything randomly, more or less. We are duplicating all of the samples in here, in this one, the smallest class, the minority class. So we're duplicating them to become like this. So we're just having like multiple examples of every example. This is the regular oversampling, the standard oversampling. Okay, guys? Are you happy, Sabil?
Yeah, so does that mean that these are known as misclassifiers? Or no?
Well, we don't know. We don't know if they are misclassified or not.
Okay.
If they are misclassified, when we compute the error, if we have just one in here that is misclassified, if without doing this, it will account for. So let's say we have 99 case here and just one in here. So if this one is misclassified, we will have only an error rate of 1%. And here, because it's the classifiers put them only on one class, we'll have here 99%, and here 1%. Yes or no? Because the classifier classified everything into class A. So the error will be here 1%, and here, sorry, the error this is 99% correct, and only 1% incorrect. So the error will be 1%, the total error. Yes? But when we multiply this, by all to make it as big as this one, we multiply it by 99. because this is only one example and this is 99 examples. So to make them the same, we multiply this by 99 times. So the error, if we classify everything into class A, the error is still 0 here, 0% here. But how much in here?
99.
99.
No, 99 only for 99 examples incorrect.
It depends how many times we multiply.
Yeah,
For example, if we multiply
99 times. It's just one case. It's 99 times this error happened. And how many times we didn't have an error here? Here they are all well classified as class A. They were all well classified. So how many correct cases do we have and how many incorrect cases do we have? How many correct cases do we have, guys?
It's 99.
99 correct cases.
Yeah, 99 correct cases because we classified everything as class A. And how many cases not incorrectly classified after oversampling?
1.
After oversampling. In the beginning, it's 1, but after oversampling?
99.
So the percentage is how much? How much error do we have? 99 correct, 99 incorrect.
99?
Yeah.
So the error rate is how much? The rate, percentage, if you prefer.
50%.
50%. 50% incorrect. So we went from 1% that was not very representative, but when we duplicated things, we got 50%. Like, because now we have like a ratio rather than, or a coefficient multiplied by this. So this is the regular oversampling. It doesn't give a lot. It just artificially increases the error by multiplying it by a number that will make this number of samples the same as this one. So we have another technique, famous one, called SMOTI. It doesn't just duplicate the samples, it can synthesize new ones. For example, let's take this example on the right side. Let's take them. And we want to oversample the red class. So we have the red and the green. This is the majority class, and this is the red class. We want to oversample it. How SMOTI works, it looks at some regions of the space where there is no majority class like in that space between this point. For example, between this dot and this dot, we don't have any majority class surrounding this this segment. So SMOTI, what it does, it synthesizes new samples of the minority class in here in this space. So let's say this is sepal length, and this is the width, let's say. So it will find ways in positioning new data points in this space, because we don't have any like majority class like that is separating every 2 dots of the minority class. Every 2 samples are not separated by a majority class. So we classify them as minority class, and we synthesize here in this space, here between the lines. You can see what SMOTI does. It draws a line between 2 classes, and if there is no majority class between these 2 lines, every segment, it just synthesizes there. It's a candidate to synthesize some point in here. And you can tell it how many points do we need to synthesize. Here we made it probably the same as this. We multiply, here we had 4, and here we multiplied the number of points in the minority class by 3. So we had 4 and we added 8. So we multiplied them by 3 to make them almost the same as the majority class. So this is how SMOTI works. It creates literally new points in the space, like in here and here. Do you understand SMOTI now?
Can you explain again, please?
Sure, yeah. How SMOTI works, it tries to create new examples but it needs to create them with values where we don't have anything of the majority class close by. So if we want to create a point in here, we don't know what it will be. Shall we put it as a minority class or a majority class? There is no point of trying to guess it in here. Yes, Miriam?
Yes, correct.
So what Smoothie does, it draws segments. It draws a segment between every 2 points of the minority class, like in here.
Okay.
And we go here, and this segment, if there is no like majority class separating it, this segment is a candidate where to synthesize the minority class. For example, here we have also another segment. We can synthesize them in here, and we can tell it how many points we need, how many new samples we need. Here we said we wanted 8 more, so we got 8 more points, and now this data, like the data points, the minority class is almost equal to the majority class.
Okay, so it's like it starts by limiting the space, and after that,
yes,
it's like, yeah, okay.
Like we can say the space of confidence, of high confidence.
Okay, I see.
And then we synthesize. Okay, guys. Okay, now the tricky part. When we mix it with the cross validation and these things, and dividing with a test set, etc. Do not oversample with methods like Smoothie on the test set. Can you tell me why? So we have the training set and the test set. So this is the whole data set. This is the training set. And this is the test set. We have like some majority class and minority class in all of them. So this advice is saying do not oversample with methods like Smoothie on the test set. Why? We have to synthesize it only on the training set.
On test set, we need a real values, real predict.
A real text, exactly.
Yeah.
If we synthesize with Smoothie on the test set as well, it means we are introducing some bias. Maybe what Smoothie is saying, like in here, what is Smoothie saying in here is not correct. Maybe this zone should not have the minority class, these places. We don't know. So with this, we are introducing some bias in the testing. And sometimes when we are generating new points, for example, we took the first example, the second one, we draw the segment, and we created a new point between them. Maybe this new point, when we do the random sampling, they will go to the testing. And these points are very close to some points in here. We have like point here, number 1, and this point. Let's call it point X and point Y. What Smoothie did, it draws a segment between X and Y and generated, like, say, one other point, one sample here. We call it Z. Maybe Z, when we do the random division, Z will go in here. And because it's so close between X and Y, it means that this testing set is highly correlated to the training set. It's almost like taking X and Y in here and putting them in here. And it doesn't make a lot of sense when we are doing this kind of evaluation. So we have like 2 problems. We are putting the assumption in the testing and maybe putting these points that were synthesized and are highly correlated to these points in here, in the testing. And this can make the testing set not a test that will describe the real world scenarios. And we will miss the generalization. Are you happy with this explanation? Are you happy, guys? Yusuf, are you happy?
Not really.
Okay. Did you get the first point? That
yes, yeah, the previous one, yeah.
The previous one, which one is that?
The slide before this one, yes.
Okay. So this one you can understand how it works. So with Smoothie, we are synthesizing points in here. So we are making an assumption that every segment between 2 points of the minority class contains points also belonging to the minority class. But we are not sure that this is real. We are not sure. It's just a guess. Do you agree with me, Yusuf?
Yes, yeah. Okay.
It's just a guess. So this guess, we don't want it to like be reflected on the testing. When I test, I want to see if my guess is right or not. So if I have points that were generated this way in the testing, it means that they are influencing my test results. But I want to see if my guess of putting points in here with Smoty is right or false. I want to test it. And to test it, I need to use a pure test set that was not, where I did not generate any new points. Okay?
Yeah.
Do you understand this part?
Yes, yes.
The second problem is that when I draw X and Y here, belonging to the minority class, so X is here, Y is here. Both are minority class, say triangles. And circles are the majority class. So when I draw a segment in here and try to put triangles as well in here between the two, these triangles that were synthesized, these are new triangles. They didn't exist in the data set. Yes?
Okay.
So these triangles might come in here. We don't know where they are. They are somewhere, maybe here, inside, maybe here. And when I start dividing, this is the training, and this is the testing. When I start dividing things, we do it generally randomly. This point that were generated, triangles, like say, for example, here, this one, and this one in here, say, let's call it T. This is not a triangle. They might go in the testing.
Okay.
X and Y will stay on the training. But X, these 2 points, T and Z, were generated based on X and Y. Yes or no?
Okay.
And they might be very close in terms of value to X and Y. So this is Z and this is T. So they might be very close in value. Because they are generated based on them. They might be close to their values. So it's a little bit like almost putting X and Y in here. So X and Y is in the test training, and another version of X and Y is in the testing. So it's like the training and testing are becoming correlated. Do you get this? It's like you are creating something based on the training and sending it to the testing, which is not good. We want the testing to be at least to some level independent of the training. Otherwise, they will be similar. It's like we will be fooling ourselves if we do that.
Yep.
So for this, we divide the data set before oversampling. We divide it into testing and training, and then we apply oversampling only on the training. And
yes, clear now.
We keep a clean testing. Testing should be as clean as possible. We can still have leakage, etc., and things that we talked about last time. It's still possible, but we want things to be as clean as possible in the testing. Are you happy, guys?
Yes, more clear now. Yeah.
Perfect.
Yes.
That means that the test set, we don't have to touch the test set at all.
Yeah, we want like to keep it as clean as possible.
Okay, that's clear.
For example, if we want to do as well feature selection with the training and the testing, shall we do it only on the training or the entire data set with feature selection based on not the wrapping, but with the filtering? With the filtering, we are looking at the feature and the class. We are looking at the feature and the class. Shall we do it for the entire data set or only for training?
I believe
yes, only for training. Only for training. Because otherwise, this feature selection step might add bias, might make my model like not generalizing. So what will happen if we use it for all? We are making the test set biased as well.
Okay.
So it's better to use feature selection only on training. If you want to use, but if, for example, if we want to use it for scaling, it's okay. If we want to use scaling, you remember scaling?
Yes.
Or normalizing. We can use, because normalizing doesn't depend on the class. Normalizing doesn't depend on the class, just we change the scale of the values. It's okay to change it for the whole set. With scaling, it's okay to change it for the whole data set. But for feature selection, because it depends on the class, it might influence also the testing. We won't have a pure testing. We want something that is pure. Well, actually, there is some problem here, but I don't want to talk about it later. Now we can talk about it later.
So that's why it's like when we start coding, we start by splitting the data and after working on the training set. Oh, okay. Because I was thinking that why we don't have to do the pre-processing on either is like on training set and test set. So now it's more clear. That means like we have to do pre-processing only on the training set. We don't have to touch.
It's better. Yeah, it's
set.
better.
Okay.
It's better to do the pre-processing only on the training set. But if the pre-processing doesn't involve the class, it's okay to use it for the entire set. If it doesn't touch the class.
Okay.
Okay. But it's better always to use the pre-processing only for the training.
I see.
It gives like a cleaner testing. Okay, guys, with class imbalance. Also, there are ways of correcting the class imbalance within the algorithm itself. Like the previous case, we have in the algorithm some ways of correcting the class imbalance. For example, like you remember last time we called this function to build an SVM, if you remember it. We put a C for value, and there are other parameters that we didn't touch. We didn't touch. We should touch only the C, the kernel, and the gamma. Where is the gamma here? There should be some. Yeah, gamma is here. There is we touch the gamma for the RBF kernel. The degree is used only for the polynomial kernel. So we touched this. We touched mainly this C, if you remember. We modified it a few times. Do you remember this, guys, in the last example?
Yeah.
Yes.
So there is this parameter, class weight. There is this parameter called class weight. And this and many algorithms has this. Many algorithms has this class weight. If you, for example, put the value class weight equal balanced here, it will automatically scale like the coefficient for each sample to its to make it like to have a weight that makes up for the class imbalance. For example, it's without duplicating. It's to avoid oversampling. Say we have class A, we have only one sample. Class B, we have 5 samples. So this algorithm, sorry, not the algorithm, this variable, if we put it to balanced, we change it in here and we put balanced instead. Sorry, my writing is a bit horrible. It's very horrible, actually. So if we put balance in here, this one, what happens is that we get a coefficient for each sample. So each sample, here, how many samples do we have here?
2.
How many samples? No, 2 classes.
Sorry, 6.
Exactly, 6 classes. So each sample 1, 2, 3, 4, 5, 6. So this is class A, and these are all class B. So this one will receive something that can compensate for its small size. So the coefficient for this sample will be here. They will stay the same, 1 out of 6. Or sorry, it will be 10, just to make it the same, to make it similar. It will be 1 out of 10. This one will be 1 out of 10, and this one will be how much? 5 out of 10. Its weight to make the sum of class A and class B the same. So if we do this, the sum of all this, it will be 1 divided by 10, five times. So it will be their sum of their weights, it will be 5 by 10. Because this one is only 1, we give it 5 by 10. 5/10. So its coefficient is 5/10, and all of these are 1/10. And this will be used in the cost function. If you remember the cost function of the SVM, or any cost function, the sum of the error. Say, let's take the regular, like absolute square error to make it simple. It's y minus y hat. Just to make it simple. It's not the SVM, it's not the hinge loss, but that's to make it simple. So we are summing all the errors, but we will still multiply every error by its coefficient. So errors are not the same. The error on this costs more than the error on this. So we multiply, if it is an error here, it will be multiplied by 5/10. But an error in here, if it is an error of 1, 5/10. But an error in here will be just 1/10 multiplied by 1. And we keep summing all the errors if we have an error in all the samples. So this is what the class weight is doing. It's giving a weight, a different weight to every sample based on its class. Are you happy with this explanation, guys? Are you happy? What's happening, guys? Silence.
It's a little tricky.
Tricky? Why?
It's like I don't understand what balance do. It's like they balancing the coefficient or what?
Yeah, let's do it again. Yeah, they are balancing the error. Let's say we are using some model that is using the mean square error, like linear regression, or this absolute square error, this one. So to compute the error, what are we going to do? Is to compute the error for every point. This is what we want to optimize. This is what we want to minimize. So we have y for point 1 minus y hat. Y hat is what we compute.
Yes.
For point 1 plus y point 2 minus y hat, absolute of course, y hat for point 2 plus all of the points. Because of this, we have only one sample of class B, and 5 samples of class B. Okay? So this error that we are computing will be focused mostly in class B. It will try to get, because if it does one operation, if it changes some weights, and these weights change all of class B's, all of these samples will be classified as class B's. Then it will do it because it will correct multiple samples by one operation. By just one modification, and classify all of this as class B. So, and because this has very little influence, then this model will try to optimize for class B more than class A. Do you agree with me?
Yes.
Because of this, we give samples in class A, like this one, a bigger weight.
Oh, okay.
5 times, or 5 divided by 10 if you want, because if they are all divided by 10, it's the same. So 5 times the weight of the others. So when we compute this, will account for more, and we try to optimize everything with this multiplied by 5. So we give like the classes, we give them the same weight, not based on the number of samples, but based on like every class is equal in terms of importance. Are you happy, guys?
I think it's more clear now.
It's clear. Okay, other guys. Yusuf, be harsh with me.
I believe it's okay.
Arda, sorry. I don't understand the coefficient. Why it's 10th and 5, which
It's
is
just
like
5 times. Is if every example in here is 5 times every example in class B. So it is 5 divided by 10. The other one is 1 divided by 10. But this division by 10 is not very important. We can remove it because if they are all divided by 10, it's the same. So this every sample of A is 5 times more important than every sample in B. We are making it 5 times more important because we don't have a lot of them. It's a bit like duplicating. It's a bit like almost the same as oversampling. Instead of doing this 5 times, like duplicating this, if we duplicate this point 5 times, it's just like we are computing this 5 times. Plus this, say again, plus this again, plus this 5 times, and adding it to this cost function that we are trying to optimize. But if we just multiply it by 5, it will be much quicker. Still not clear? Amal?
I think it's clear. Thank you.
Sure, you are sure, not Yusuf?
Yes, yeah.
No, not really.
This is a yes with a lot of hesitation.
There
I'm
needs
just thinking, and yeah.
one more explanation, I think.
Okay, let's add one layer of chocolate. So, do you understand what we are doing in here? Without this 5, do you understand this?
Yeah, it's just we are calculating errors, so it's
errors with every part,
we take
summing them.
the absolute value of of each predicted value.
Okay.
Yeah.
We are computing all the errors for every point. But this error generally belonging to the same data set, to the same class, tend to behave the same. So if my model doesn't find a way to divide like this point from the others to classify them differently, it can't find it. What it will do you think? Say we are using an SVM, a linear kernel. It means that there is no kernel, but it's like that. Here, 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 and here we have a triangle. We will never be able to put like a line between the two. We can't. Do you agree, Amal?
Yes.
It's not linearly separable. So what do you think our model is going to do? It wants, because we have 5 points in here, circle, and only one triangle. What solution is probably going to be? What hyperplane we will have?
So is it for the kernel you're saying?
No, there is no kernel for now. We are using the regular SVM with a linear kernel. With a kernel, we can have a solution, but with the with the SVM, with a linear kernel, and we are trying to have, like, say, a hard margin SVM, and we are trying to have a hyperplane that divide the circles from the triangles, but it doesn't exist. That line. This line doesn't exist. There is no line that can divide circles from the triangle. So my model is going to do what? It will be this line. Which one is the best one that will give me the best results in terms of accuracy without any coefficient, without doing anything? Which one? Is this line? This?
The triangle.
What do you mean by triangle? What line? This line will divide these guys into one class and these guys into another class. These are in the wrong class, probably.
You cannot choose any line.
They can't.
It will be something like this. We cannot choose any line. It will be this class A, class B, sorry, and class A where we don't have anything. So what does it mean? We call it it will default. It means it will classify everything as class B. This is the best outcome we can hope for with such scenario. We will classify everything as class B.
Yeah.
But if we add the coefficient, we classify everything as class B because we want to minimize the error. And the error is to classify most of them in its right class. So this one will misclassify this and this. This line will misclassify this, and this. This line will misclassify this, and this. But if we take this line, it will misclassify only this. Yes? Yes or no?
Yes.
Yes.
Yeah, it will misclassify only this.
Yeah.
Only one case. So it will probably do this with a hard margin SVM, let's say. But if we add the coefficient, this error will account for 5 errors, and this only 1. Then we will not have this line, because we will have 5 errors if we do this line. If we do this, we will have 1, 2, 3, 1, 2, 7 errors when we sum the error. This one will also have 7 errors. So what we can do is something like this. So this thing will have, remember, this is class A. Sorry, it's really awful now. And class B. So this one, how many errors do we have like that? When we draw it like in here?
2.
How many? Just 2.
2.
Just these 2. Yes, just these 2. So that's why we are giving some balance to the problem. We are balancing my data set. So when we add this coefficient, 5 multiplied by this error, and the other all remain the same, we are having like at least a better solution than what we had before, because this one doesn't mean anything. And this, so here we can more or less classify the second class. If the second class is important, we are able to classify it with some accuracy. We are making some errors in the class A, but in class B, we are having it with some accuracy. So this is why we add this coefficient. Is to multiply the value of the point. It's unique, so unique that we want to multiply its value to get a better outcome, to classify, to get a better classifier, a better model for class A. And this is when you think that class A is as important as class B. If it is not, you can have different coefficients. Like here, class weight, you can put balanced, which will be automatic. But we can have a dictionary that will give every example a personalized weight that you specify, in case that you think that the examples are all different in this case. Are you happy with this explanation, guys?
It's more clear.
Yes.
It's clear, okay. And our others,
Yes.
Yusuf, Amal.
Yes, thank you.
Perfect. Yusuf.
Yes, yes.
Okay, when Yusuf says yes, I'm happy.
Good.
because you always say no when you are not.
I give you headache.
No, I'm happy with headaches. That's fine. Better to have it now. So this is for class imbalance. This is a rather simple thing. I don't want to dive too deep in it. It's with when we deal with missing data. This is the last topic, guys. Don't worry. About to close for today. So when we have missing data, so for example, let's have a look at this data set. Sometimes we have fields that are missing. This, and this 4 are we don't have, for some errors. For some, we had some problems in measuring them, or we lost them, or whatever. So there are cases where we have missing data. So what do we need to do? We can just ignore, if you have a large data set, you can ignore these instances where you have missing data, missing fields. You can ignore this, this, and this. But it's not a good idea when the data set is small. So this is by ignoring. The second solution is to guess these missing values, to guess them by some way. We can do the mean imputation. And when it is, we have an interrogation point, when we have something missing, we compute the mean or the median value in here, or the maximum. So there are other ways. The maximum value, the mean, if there are numbers, we can compute the mean in here, and put it in here. The median as well is a possibility, the maximum value, the one that is repeating the most, and put it in here. We can also keep this, sorry. We can also use missing, and this interrogation point will be treated as a separate value. We can also use that. It's like we have red, green, yellow, brown, orange, and unknown as a separate value. It's like a color, but not a regular color. You understand this? It's like we treat it like a separate color that we can't see. Same for shape. We treat it as a shape, like an interrogation shape, and this one will be equal. But we can't, we don't know what it is, but it's a shape, like an hypothetical shape. Okay, so this is another possibility. Are you happy with these two possibilities? Using the mean value and the most likely value, mean, median, max, or treating the interrogation mark as a separate value altogether, an extra value. You got these two possibilities, guys.
Okay.
They are fine, very easy.
Yes.
Perfect. And we have also the imputation by regression. By regression, it means we compute this value based on this and this possibly. So we build a model like that can predict these values based on the other values in the same line. It's like building models. A model for this, a model for this. And this model will treat this class, this row, as the class, and the others as the predictor, and try to figure out whether by regression, if it is a number, or by classification, if it is a class like this. So we can try to figure out color based on cone and vegetable. So this shape and class, and we try to predict this. So this is one classifier we build, one model we build. Same goes for shape. And we try to predict this value based on the others. It's just ways. All of these methods are not perfect, guys. It's just ways in like coping with this problem. Are you happy with this also?
Good, good.
Perfect.
Yes.
And there is also another way. Some learning algorithms offer mechanisms to handle missing data out of the box, like the decision trees. Decision trees can allow this way, something that is missing, it can treat it automatically as in here, when we said we keep the interrogation mark as a separate value, an extra value. Decision trees can do that, but it can also, like when it has an unknown value, it will go to both directions. When we have this, for example, decision tree like this, and here we have the leaves. If, for example, when we go, let's say we have here the leaves. These are the leaves, the classes, class A, class B. If it comes here and it finds a missing value, what it does, it goes into both directions. But at the end, if it goes to both directions, it will end up with two leaves. For example, if we have a leaf in here, it can end up in here and in here. Because here we have we don't know the value, so we go to both, and then see the probabilities in both nodes, and aggregate in some way the two probabilities. But this is a circle. If we have two classes, a triangle in here or a circle in here with probabilities, it will aggregate the values, the probability values in both nodes. This is the decision tree way, one of the algorithms actually in the decision trees, that is like how it deals with missing values. Are you happy with this explanation, guys? It's very simple. Don't take it too complex. When we have a missing value, we go into both directions, and we keep going normally with the rest until we reach the leaf. The leaf will tell us the class, And this, but we have two leaves. And we mix them, we mix the probabilities to see what class we are going to. Very simple. Are you happy, guys? Are you happy, guys? No. This is a clear no. But guys, tell me, where is the problem? What don't you understand?
Reda, it's clear, but if I remember it.
If you remember what?
Yes.
The decision tree.
No, this is it's clear. What we said, you said, it's very very clear. But if I could remember it, if I remember it later.
Oh well, that's another thing. But I mean, what I'm talking about here, how one of the algorithms of decision, how it is, and how it deals with missing data is clear in this sample, this example.
Yes.
Yusuf, Amal, Salsabil.
Yeah, Reda, sorry. I was expecting from you to say, for example, for the yellow fruit and for the cone vegetable. So just one, it's just one feature like missing, but for the fruit, both features are. It's really hard to predict like both of them, or like it's.
Oh yeah, this one is we will have, but that's fine. You can ignore this. Can you like understand how, for example, when we try to classify this with the decision tree, say we built a decision tree based on the data set, and we want to classify this case.
Yes, yeah, definitely.
So what happens? There is a building of the model with this kind of problems. We are going to have a look at it later. But when we try to like classify this, we go into both directions. So here it is yellow, and we go here. We don't know it, so we go here and here. And once we reach the leaf, we see the probability of the classes, and we mix them and see which one is the more probable class. This is how we deal generally in classifying a sample that has something missing. It's very simple. There is nothing like magic in here. It's like when you don't know the road, you try them both, and you see the outcome of both roads, and you try to get some average value between them. Like in real life, when you go like to you want to like go to some place where, for example, it's not raining. You try and you go to like two roads, but there is no sign. So you try them both, and you evaluate how, like this example that evaluate the map based on these two directions. So you have to consider like all the values. Yeah.
In this case, we can consider each level of the tree as features.
Sorry, I couldn't hear you.
In this case, we can consider each level of tree as features.
Yeah, generally in the decision tree, each level is dealing with the feature. Yeah. But we can have like the same feature repeating here. For example, if you have a feature in here, it can be repeated in here because they are independent. This is like the decision tree. I think when we reach, or maybe next time, we are going to revisit it again because we are going to study some more complex models that are based on the decision tree. So we are going to have a look at it again. Are you happy with like the two roads explanation, guys?
Yes.
We take both roads and see the end, and we try to average the ending and see which what class it is. So if in here, for example, in here, we don't know its shape, so we go both when we reach the shape level, we go both roads, and at the end we see the probability of fruit. If it's say probability for fruit, it's 90%. Probability of vegetable, it's 50%. When we aggregate the probabilities, it's going to be probably the fruit. For example, that's just an example. Okay, guys?
Sorry, Rida, when we impute by the mean, okay, it's simple when we have like regression, but when we have classification, let's say that we have 3 classes, that means like that there means how to choose the class, the mean of classes.
There is no mean of class. That's why I said
yeah,
like
so,
see more.
Yeah.
Yeah, there is no mean of a class. You can.
So only for regression, mean and median.
Yes, only for numbers. Yeah, but for classes we can't have.
Yeah.
There are ways of converting this red, for example. If you find a way of converting red, green, yellow to numbers, like the RGB code or something like that, but it might be possible, but not always.
Mm-hmm.
Okay,
we can
guys.
do it with word2vect.
With what?
Word2vect, maybe you can use it in deep learning.
Yeah, but for word2vect, you're assuming that these words have the same representation as what we used for word2vect when we reach this case. But it is a possibility, yeah. If you think word2vect is a good representation of this class space, then it will be a good solution. But not always. Not always it's the case.
Depends on the case, yeah.
Yeah, in some cases it might be not representative of this color meaning. Because it's like context dependent. This color may be contextualized. Are you happy, guys? I think we reached the end of the session for today. Yes.
Thank you, Reza.
Thanks a lot.
Thank you.
Thank you, Reza. Thank you, everybody.
No problem. Guys, maybe next time there won't be a session. I will confirm it with you.